Alright, so this is NCCER Instrumentation 4, Module 7, Analyzers and Monitors. So these are going to be a lot of different types of devices that can take different readings, and usually it's going to have to be some kind of chemical makeup. Like most people know, the lab for this is doing a pH lab where you're testing the pH of different chemical or different Coke, water, different acids and bases and stuff like that. Ton of trade terms on page 1. The only one that I have highlighted is the parts per million, about halfway through on the right side, as an online test question. Parts per million gets hit with the online test question. The concentration of solute in a solution is expressed as parts of solute per million parts of solution. Moving on to page 2, 110, the science of matter. I've got the third sentence highlighted. The smallest particle of matter with a distinct chemical identity is the atom. I don't know why I decided this stuff would be the best last chapter for Instrumentation 4. That's what they did. The immediate next sentence is a separate highlight. Atoms contain up to 3 different particle types: protons, neutrons, and electrons. It's probably going to be a good idea. I don't think I have them highlighted, but knowing that protons have a positive charge, electrons have a negative charge, and neutrons have a no charge is going to be good to know. I can see them pulling that as a question. I don't have it highlighted, but still good to know. Elements 111. Right hand side of the page, the sentence that has atomic number, the one after it is highlighted. Since each type of atom has a unique number of protons, elements are also identified by a numeric value called the atomic number. The atomic number corresponds to the number of protons in the nucleus of an atom. Immediate next paragraph, first sentence is highlighted. An element's atomic mass, also called the atomic weight, is an average based on the masses of different isotopes of the element. They go through the periodic table. Hopefully everybody's seen that before. You're going to need to know, if you flip over to page 4, you're going to need to know what some of the different parts of the periodic table. So page 4, first paragraph, last sentence is highlighted. Each period in the table ends with a very unreactive gaseous element called noble gases. So that's like your helium, argon, argon, I forget what the other ones are. Xenon. Like these are unreactive gases. Like that's why you would use argon for welding and stuff like that as a shielding gas, because it's non-reactive. But you need to know that the periods are the horizontal rows. The horizontal rows are the periods. And then you need to know the vertical rows are called groups. So periods, horizontal, vertical is groups. I don't have either one of those highlighted, but it's the first 2 sentences of the first 2 paragraphs. I can see them pulling from those. The whole third paragraph is highlighted on page 4. The elements within a given group behave in similar ways chemically. For example, sodium and potassium are very much alike. That's why potassium chloride can be used by people with high blood pressure as a replacement for sodium chloride. Table salt, it tastes and behaves similarly but contains no sodium. Compounds, first sentence is highlighted. Elements combine together to form substances known as chemical compounds. Out to the side I wrote example H2O. Oh yeah, I figured I have slides on this. So that's the period. So even though they don't have but 2 elements in that period, that horizontal row is still period. And then you have your groups that go vertically from left to right. Chemical reactions, 120. Oh, I forgot this guy. There's like 600 PowerPoints for this Chemical reactions, first sentence is highlighted. The chemical reaction centers upon the atom's outermost electron shell, known as its valence shell. Remember, probably all the way back to, well, if you took electrical, the valence shell is what has your outer electrons, so that's what actually moves with electricity, is the sum of the electrons in your valence shell. That's what, like, the number of electrons in your valence shell, that's what makes something either a conductor or an insulator or a semiconductor, but those are what physically moves whenever you push voltage through something. So I'm on page 4 of that last chapter. I am recording this. We're just going through this. Page 4, 120. Same paragraph, last sentence is highlighted. When atoms react, they tend to gain, lose, or share electrons with other atoms in order to complete their valence electrons. One, two, one. Chemical bonding. Second paragraph, first 2 sentences is highlighted. When a metallic atom reacts with a non-metallic atom, an electron gets transferred from one atom to the other. The process links the atoms together in what is called an ionic bond and forms an ionic compound. So you're going to need to know what an ionic bond is, like what it's made up of, when it's metallic atoms reacting with non-metallic atoms. Next paragraph, first 2 sentences are highlighted. When 2 non-metallic elements react, they share electrons between themselves, essentially passing them back and forth. This process forms a covalent bond. So you need to know what an ionic bond is and a covalent bond. Flipping over to page 7. That last paragraph in that section right above 122, everything except the last sentence is highlighted. Finally, metal atoms can form bonds with each other in which the valence electrons get shared among a huge number of atoms to form a kind of electron sea. This type of bond is called a metallic bond. So metal to metal, metallic, non-metallic, to non-metallic is covalent, and non-metallic to metallic is ionic. Kind of what you want to key in on for those. 122, top right of page 7. First 3 sentences are an online test question. A mole consists of 6.02 times 10 to the 23rd particles. These may be atoms, formula units, or molecules. 1 mole of any element has a mass in grams equal to that element's atomic mass value. So a mole is a measurement of an atomic mass. That note right there would explain that a little bit better if you don't remember what a mole is from chemistry. Behind, flip it over to page 8. Concentration, 130. That's probably the end of 9. Concentration, second paragraph, last sentence is highlighted. Got a couple questions that come out of this highlight. 2 terms commonly used to describe the concentration of a solution are molarity and parts per million. That's 130, second paragraph, last sentence. 2 terms commonly used to describe the concentration of a solution are molarity and parts per million. You're going to have a question to figure out the molarity of something. I've just got step 3. Really, it's just the equation in step 3 is highlighted on the right-hand side of page 8. Molarity equals moles of a solute over liters of solution. They're going to give you a couple numbers. You're just dividing it out. Easy stuff. Yeah. 140, acids, bases, and pH. I swear if they made this. Second sentence of 141 is highlighted. A charged particle is called an ion. A charged particle is called an ion. acids and bases. 142, third paragraph, it's going to be everything except the last sentence is highlighted. An acid is classified as strong if it ionizes into a lot of hydrogen ions that form hydronium ions when added to water. For example, hydrochloric acid ionizes essentially 100%. Consequently, it's a strong acid. Acetic acid found in vinegar does not ionize completely. Only a small percentage of the hydrogen turns into free hydrogen ions. Consequently, it is a weak acid. pH 143. First sentence is highlighted. Convenient way to state the acidity or basicity or alkalinity of a solution is the pH scale. That's the pH scale at the bottom of the page. Skip a sentence. The next sentence is highlighted. As the quantity of hydrogen ions increases, the solution becomes more acidic. So you add more hydrogen ions, you're going to become more acidic. Second paragraph, first sentence is highlighted. The pH scale typically ranges from 0 to 14. I don't have any of the other stuff for that highlighted, but you need to know. So 7 is neutral. Anything below 7 is acidic. Above 7 is basic or alkaline. But another thing, I know I probably said this last semester when we did the lab for it, but like going from 6 to 5 acid-wise is not like just barely bumping up. It's exponentially higher than this. So the pH scale is logarithmic. Each unit represents a factor of 10 change. For example, a pH of 9 is 10 times as basic as a pH of 8. So every single time, like 3 is 10 times as acidic as 4. So it's not just like gradually, literally moving up. It's spiking crazy fast. So everybody should know, at least everybody should know the pH scale. It's not too hard. 144, neutralization of salts on page 10. I've got the last sentence of the first paragraph highlighted. Salts are electrolytes, as are acids and bases. Salts are electrolytes, as are acids and bases. Moving on to section 2. Analyzing physical properties. So the by far the biggest trade term in this section is the specific gravity, because the more and more I hear about the plants and stuff like that, we talked about these big tanks, right? And they have their if they're closed off, they have a high and a low pressure side. This would be my low, this would be my high right here. And this might be, you know where we've talked about where stuff has like a wet leg or a dry leg? I have come to find out that's a little bit of an old terminology thing. What they're doing, huh? Suppress? It might, so they're called capillary tubes. And what they are is it's just a tube filled with oil, and they look like they have the flange disc, like it has a flange like this, and then it just has a disc in here, and all it is all it is you push on this, and you're pushing on oil in the tube, and then you come down to a DP. So say you have a oil-filled line coming into here, and then your high pressure coming into here. All you have to know is the specific gravity of that oil in order to determine like a level inside of that tank. So like a lot of these DP sensors, they're not doing like you guys learned how to zero and span the differential pressure transmitter, or at least a lot of y'all have. They're not filling these. You're not filling these big tanks outside at these refineries all the way to the top so you can span them. Usually you're just you're taking a zero at atmosphere, and then you put the specific gravity in, and it calculates what these spans should be. And that's how they're zero and spanning these things, as I'm coming to find out, which is way easier than using a wet leg or a dry leg. So definitely need to know what specific gravity is. 210, density and specific gravity, you need to know that equation. Density is mass over volume. You need to know the specific gravity equation. Specific gravity equals mass of a specific volume of substance over mass of the same volume of water or air. Between those two equations, there's 5 questions throughout the reviews. 211, hydrometer. First sentence of 211 is highlighted. One way of measuring the liquid's specific gravity is with a device called a hydrometer. 211, first sentence of that paragraph. 212, air bubble measurement. Anybody remember talking about a bubbler at all? Sometimes I can't remember if I've talked about stuff or not. I'm going to give you the highlight, then I'll talk about it. First sentence of 212 is highlighted. The simplest and perhaps most widely used method of measuring density and specific gravity in a process is usually bubble test and reference chamber in conjunction with differential pressure transmitter. So they can actually tell, like if, say I had a straw and I stuck it in my mouth and I just blew through it, pretty easy to blow through it. If I had a 10-foot long straw and I stuck it at the bottom, all the way to the bottom of a 10-foot cup and I blew in it, it's going to be harder to blow through than me just blowing through a regular straw. And by those differences in pressures, they can use a DP transmitter to determine specific gravity. So we're in module 7, page 13. My next highlight's going to be in 213. First sentence is an online test question. 213, displacement measurement. A displacer is sometimes mistakenly called a float. So whereas a float moves up and down, like whenever it's down, it's usually a normally open condition. Whenever it's up, it's closed. Most everybody, if you've done the temperature labs in the back, I've pointed out the float that is for the hot water tank. That's a float. This displacer, a lot of people get this confused. This displacer doesn't move. It works on the principles of buoyancy. So there is pressure pushing on the bottom of this, and it can take a force equation and tell a level measurement based on the amount of force pushing on the bottom of it, rather than actually moving. Like there's probably going to be a little bit of movement in this, but not like a float moving up and down. Densometer 214. The first 4 sentences are highlighted. 214. Measuring the density of gases is important in the gas transmission in petrochemical industries. The measurement can be accomplished using a densometer with a probe. The probe includes a vane that is installed in the pipeline that consists of the flowing process fluid. The vane oscillates in the fluid, causing the acceleration of the flowing process fluid. Causing an acceleration. Moving on to page 14. I don't have anything in the 215 nuclear detectors. You can read through those if you want, but they can use nuclear radiation to determine density. Viscosity 220, right hand side of page 14, first full paragraph, first 2 sentences. Of all the physical conditions, temperature has the greatest effect on viscosity. An increase in temperature causes greater separation among liquid molecules, a reduction in the shear stress, and therefore a decrease in viscosity. So an increase in temperature causes a what in viscosity?
Decrease.
Decrease. Viscosimeters 221, first sentence is highlighted. Viscosimeters are instruments used for measuring the viscosity and flow properties of fluids at ambient or other specified temperatures. Next paragraph, first sentence. A falling ball viscometer measures viscosity by measuring the time required for a ball to fall through a specific distance of liquid under test. If you flip over to page 16, you can see this picture on here. So pretty much you just have a little metal ball. Whatever your liquid in your tube is, you put it as a set distance and then time it however long it takes. You can measure your viscosity based on how long it takes to get to the bottom. Turbidity 230. First sentence of turbidity, you have two questions coming out of that one sentence. The cloudiness of a fluid caused by suspended particles is called turbidity. Some of this stuff I'm not going to talk about too much because, one, I've never seen it, and two, I think it's going to get very specific on like what stuff that I don't think instrument techs are going to be messing with. This is more for chemists, in my opinion. 232, page 17, the whole first paragraph is highlighted. Transmission turbidity analyzer, which is what's at the bottom or up there on the board, contains a light source, lens, sample cell, photocell, and control unit with a readout. The lens focuses a light from the source through a sample cell, which is measured by a photocell. Liquids with low turbidity absorb and reflect very little of the light, so the photocell's output is high. Liquids with high turbidity absorb and reflect a significant portion of the light, so the photocell's output is low. The control device amplifies and transmits the photocell's output signal to the readout device. Out to the side of that, I wrote uses light to measure turbidity. Pretty much the main thing you need to have for that one. Moving on to page 18 and 19. Ratio analyzer 234. The first two sentences are highlighted of 234. The ratio turbidity analyzer uses a more complex system to measure turbidity, sharing technology from both transmission type and reflection type analyzers. See figure 22, and the light from the common source passes through a rotating chopper disc. Key in on the rotating chopper disc that alternately blanks out one light beam at a time. That's all I've got for section 2. So take a few minutes and see if you can answer those 5 questions on page 20. Alright, so section 3. Analyzing chemical properties. This next one is a more missed question, usually on this test. The flash point trade term is highlighted. So that is the lowest temperature at which a liquid gives off vapors that will mix with air and be able to ignite. Next highlights in 310 flash point determination. First sentence is highlighted. OSHA defines flash point as the lowest temperature at which liquid gives off vapor within a test vessel in sufficient concentrations to form an ignitable mixture with air near the surface of the liquid. The rest of the paragraph is a separate highlight. Closely related and less common term associated with flash point is the term fire point. You want to make sure to have these differentiated in your head. This is defined as the temperature at which the flame becomes self-sustained and continues burning the liquid. At the flash point, the flame does not need to be sustained. This last sentence is the way you want to key in on. The fire point is usually a few degrees above the flash point. So you can have a spark at a lower temperature than you can have a fire. That's pretty much all they're saying. Moving on to page 22, in section establishing the flash point. First paragraph, second sentence is highlighted. You can use the rapid flash test system to quickly determine if a flash point occurs below or above a specific temperature. However, it does not find the actual flash point temperature. You need to know that the rapid flash test does not find the actual flash point temperature. The immediate next sentence is an online test question. The auto ignition system works at extremely high temperatures. Measuring pH. I'm going to go through these. I'm going through a lot of this pretty quick, but I'm going to go through this pH stuff somewhat quickly because most of y'all have already done it. The whole first paragraph of 321 is highlighted. I've got 3 separate questions that come out of the paragraph. Most of it's keying in on the last sentence. 321. As shown in figure 23, the numbering system for pH scales from 0 to 14. Value of 7 at the center of the span indicates a neutral solution. The values below 7 represent acid levels, with the smaller numbers indicating the highest acid levels. The numbers above 7 represent the base scale, with the larger numbers indicating the highest base levels. You need to, what's that?
Key in on that last
Key in on that last sentence. The numbers above 7 are basics, and the larger you go, the more basic or alkaline it gets. pH probes. I can show you all the probe again. I just got another big one from PBF that's sitting on the table, and I haven't messed with it or anything. Like the pH probe y'all used last time was like not a lot bigger than this. This one's a desktop unit, probably a little bit more accurate. Used to taking more readings and stuff like that, but yeah, I can get that out if people want to see that stuff again. First paragraph of 322, the last 2 sentences are highlighted. Other systems use 2 physically separate probes called a pH electrode and the reference electrode respectively. In either case, the actual technology involved is much the same. The next paragraph is highlighted and continues on. It's the whole paragraph. The whole next paragraph is highlighted. pH probe is often viewed as a battery whose voltages varies with the pH level of the solution. This component is sensitive to hydrogen and is often referred to as the measuring half cell. Special glass tube or special glass bulb or membrane material allows hydrogen ions to pass into the tube. When the pH electrode is placed into the solution, a voltage proportional to the hydrogen ion concentration, key in on that, develops between the inner electrode and the outer electrode or glass bulb material. I don't know if y'all remember that that probe, but it had a glass bulb on the end. Like I think it's got like a metal rod, a glass bulb, and something else. I'll get it out here in a little bit and pass it around again. Calibration and compensation. 323, first 2 sentences are highlighted. Due to the way they work, pH electrodes require regular calibration. This is accomplished by using a buffer solution. Again, y'all remember doing the test and I had those 3 little packets and I made buffers. Like the buffer solution was, I had a 7, I had like a 5, and I had an 8 to make a base and an acid. Like that's how you make a known, and then you stick your pH probe in there and then you calibrate it to that known. That's how you calibrate a pH probe. But you do that with a buffer solution. But that's just, the ones I mess with are all powders that I mix into water. And they can create an alkaline or an acidic concentration of a known concentration. Moving on to page 26, 330. Conductivity, measuring conductivity, whole first paragraph's highlighted. A pH measurement system is designed to be sensitive to just one ion, the hydrogen ion. Similar systems can be designed to measure other specific ions. There are applications, however, where it is necessary to determine the total concentration of all ions. This can be accomplished by measuring the solution's conductivity. So we're going to stick plates inside of a sample solution, and they can measure the conductivity because if they have a known amount of resistance and distance, they can determine the conductivity of whatever's in that solution. The paragraph that's right before that little equation, first sentence is highlighted. Conductivity is sometimes referred to as specific conductance and is defined as the reciprocal of the resistance of a 1 centimeter cube in the solution at a specific temperature. 332 additional factors in measuring conductivity. First sentence is highlighted, bottom right of page 26. Temperature strongly influences a solution's conductivity. So they'll usually have some type of RTD or a thermocouple on there that will make measurements, and they'll have correction factions in the unit itself to correct for temperature. 340. Measuring oxidation reduction potential. This is usually a more missed question in these chapters. The first paragraph is highlighted, keying in on the first sentence. Oxidation is the loss of electrons by an atom, molecule, or ion, while reduction is the acquisition of electrons. Every liquid has both oxidizing and reducing ions, but their balance varies from liquid to liquid. Those with extra electrons are called reducing agents, while those that have a shortage are called oxidizing agents. Next paragraph, first sentence, separate highlight. The oxidation reduction potential, ORP, of a processed liquid indicates by its voltage polarity whether the processed liquid has an oxidizing potential or a reducing potential. They go into the ORP instruments. The first, the end of that started paragraph on page 28 is highlighted. A port is provided for replenishing the potassium chloride, and a rubber sleeve protects the port from contamination.
What is that?
It's the first full sentence on 28.
Oh.
A port is provided for. They're just talking about the ORP instruments. And you can see the assembly on figure 33 right here at the top. They're just saying that, let me show this. Potassium chloride. Reference electrode contains potassium chloride. Yeah, this is filled with potassium chloride and then has a rubber seal over it. So, take a few minutes and you got section 3 review on page 30. Section 4, gas analyzers. They'll have like the THC, total hydrocarbon content. If you've been in P-Tech, you've probably heard that quite a bit more than you ever have over here. They talk about that a bunch with your hydrocarbon amount of hydrocarbon content in different gases and stuff like that. My first highlight is 410, first sentence. The demand for oxygen or O2 analysis is due in part to the essential role that oxygen plays in the combustion, oxidation, and other industrial process applications. First sentence of 410. 411. High temperature electrochemical sensors. Second paragraph, first 2 sentences. One type of high temperature electrochemical sensor commonly used in combustion control applications to determine the combustion, key in on combustion efficiency, is the zirconium oxide oxygen sensor. This sensor consists of a cell made of ceramic zirconium oxide combined with an oxide of either iridium or calcium. I'm pretty positive this is, everybody heard of having like O2 sensors on your car? I'm pretty sure this is how they work. Like they're using that zirconium oxide to see how much oxygen is in your exhaust to tell how efficient your engine is running. But it has to be high heat usually. Page 32. That middle paragraph from the section coming from 31, right in the middle of it, I've got an online test question. One disadvantage is that the zirconium oxide cell has a relatively short life, typically less than 18 months. So that must not be the O2 sensors last longer than that. Um, 412, paramedic analyzers. The sentence that's before the bullet points is highlighted. Paramedic types of oxygen analyzers are most commonly used in the following applications, and I highlighted the medical application, second to last bullet point. (413) galvanic sensors. First sentence is highlighted. The galvanic oxygen sensor, also called coulometric oxygen sensor, is a chemical cell whose oxidation reduction potential (ORP) is changed by the introduction of a sample or of the sample gas. Measuring carbon monoxide. Carbon monoxide. First paragraph of 420. I'm going to have the last sentence in the bottom left of page 33. I've got 4 questions that come out of that one sentence. One such byproduct of combustible gas is carbon monoxide, which is a colorless, tasteless, and odorless gas that combines with the hemoglobin of the human blood and inhibits its oxygen carrying capacity. That's why y'all always hear, like whenever power's out and stuff like that, do not run your generators near doors or windows or anything like that, because that carbon monoxide off the exhaust, you don't smell it, you don't taste it, nothing. Like once it's in you, they can't get it out. Like it deprives all your blood of oxygen. Measuring carbon dioxide, 430. Anybody work anywhere where they have to wear a 4-gas monitor? Probably will. For you guys that are going to refineries and chemical plants, you're probably going to have to wear, not quite as big as the picture on 33, but I always had to wear had oxygen, carbon monoxide, carbon dioxide, and something else on it. You had to wear that. It was required that we wear it all the time, just to make sure that you didn't go somewhere where
Oh, I think we got some of those. This little yellow thing that makes a buzzer sound when you get too close.
there's a bunch of different ones that,
Yeah, is it a clip-on thing though?
yeah.
Yeah.
They can have some that aren't even like battery powered, and they just like a card that changes different colors if you go in somewhere you're not supposed to, or if it doesn't have enough oxygen, stuff like that. Measuring carbon dioxide. First 3 sentences are highlighted. Carbon dioxide, CO2, is a non-flammable, colorless, odorless gas, somewhat heavier than air. Carbon dioxide is one of the gases that make up the Earth's atmosphere, along with nitrogen, oxygen, and argon. It's a greenhouse gas, along with methane, water vapor, and many other gases. This is a dumb highlight. Out to the side of that, I wrote oxygen, not a greenhouse gas. Out of that highlight, they want you to know that oxygen is not a greenhouse gas. Third paragraph. First sentence is highlighted. Carbon dioxide is non-reactive or inert with many materials and is commonly used for applications such as blanketing and purging of tanks and reactors, and is a shielding gas in arc welding applications. So you can use CO2 as a shielding gas for arc welding. The last sentence of that paragraph is a separate highlight. At extremely low temperatures, carbon dioxide solidifies into dry ice, which is often used to freeze and preserve foods. Frozen CO2 is dry ice. 440. Measuring hydrogen sulfide. I've got the first 3 or 4 sentences highlighted. Hydrogen sulfide, or H2S, is a colorless, very flammable gas. In low concentrations, it smells like rotten eggs. It is heavier than air and very toxic. After very few minutes of exposure at 100 parts per million, people lose their sense of smell and can no longer detect the presence or absence of the gas. Top right of page 34, that first full sentence in the top right is highlighted. Anabolic decay, aided by bacteria such as occurs in sewers, produces hydrogen sulfide. If you're ever around like gas pipes and stuff like that, like if you're ever replacing a toilet or a vanity or sink or anything like that, like the sewer smells that you're smelling are not good. Like you're supposed to like clog that stuff up with a rag or stuff whenever you're doing plumbing work, because hydrogen sulfide can be built from shit. 441, personal protective indicators. This is what I talked about. Second paragraph, first sentence is highlighted. One very simple device is a wearable personal protective indicator that changes colors when exposed to toxic gases, including hydrogen sulfide. So they can have different ones: personal protective, semiconductor sensors, electrochemical sensors, different ones. But that's the only one I have a highlight in. 450, hydrocarbons, measuring hydrocarbons. Top right of page 35, first 2 sentences are highlighted. Hydrocarbons, compounds composed of hydrogen and carbon, are present in many forms in atmospheric air. Among these substances are methane, has a concentration of approximately 1.7 parts per million, which accounts for the majority of the concentration of hydrocarbons. Down at the bottom, 451, first sentence is one highlight. The instrument most often used to measure vapors for total hydrocarbon content uses the principle of flame ionization detection, or FID. The next 2 sentences are a separate highlight. For this type of detector, an air sample and a fuel hydrogen are sent to the burner nozzle at a controlled flow rate. The concentration of hydrocarbons is determined by ionizing the hydrocarbons. You want to key in on that sentence. The concentration of hydrocarbons is determined by ionizing the hydrocarbons in the flame and then measuring the generated ion current as shown in figure 40. Take a few minutes and answer those 6 questions on page 36. Other analysis techniques. 510, first sentence is an online test question. Clean rooms are specifically built in closed areas that are specially designed to control airborne particulates. Key in on that airborne particulates. Temperature, humidity, airflow, patterns, air motion, and lighting. Optical microscopy. Second paragraph, last sentence. It's like the last 5 lines of the second paragraph, 511. For example, one method specifies in the federal standard for counting and sizing the concentration of particles 5 micrometers and larger in clean rooms is to collect the particles on a membrane filter and then look at them through an optical microscope to count them. Page 38, 512. Discrete particle counters, DPCs. Third paragraph, last sentence is highlighted. Two types of DPC instruments are optical particle counters and the condensation particle counter, CPC. Last paragraph, before 520, first sentence is highlighted. The top right of page 38. The condensation particle counter, CPC, operates by saturating the heated sample particles with butanol, which is evaporated into the airstream, and then cooling the sample with a condenser, or in a condenser.
You still have 3 points.
520, determining chemical composition. 521, gas chromatography. Top left of page 39. I've got 3 highlights in the end of that first started paragraph. The first full sentence on page 39 is my first highlight. Chromatography works on the principle that when a test mixture is processed through the analyzer, the different components that form the sampled mixture separate and exit the chromatography process at different rates. Key in on that last part of that. The rest of the paragraph is a separate highlight. This separation allows the individual components in the sampled mixture as well as their concentrations to be identified. Skip a paragraph in the first 2 sentences of that bottom left paragraph are highlighted. The chromatography process involves 2 phases, mobile and stationary. In the mobile phase, the sample mixture to be analyzed is first vaporized, key in on the vaporized, and combined with a moving stream of carrier gases such as helium for subsequent passage through the chromatography column. Right-hand side of page 39, second paragraph on the right-hand side, first 2 sentences are highlighted. In some gas, how many times did I make me say that? Somebody say that the right way?
Chromatographs?
Huh?
Chromatographs?
Chromatographs? That's it, chromatographs. Packed columns have been replaced by capillary columns. Capillary column is basically a very long tube which generally has a very small inside diameter. Page 40, 530. Measuring infrared radiation. 531, basic theory. Okay, so the first and second sentences are highlighted in 531. The second sentence is also an online test question. So they use their section review as an online test question. Thermography is the technique of using an optical and electronic system to convert invisible infrared radiation into visible light. Next sentence is the online test question. Thermography is based on the principle that any object having a temperature above absolute zero will emit some infrared radiation. So remember on the color scale, like if you're looking up here on the board, this is the amount of visible light we can see. Very little. That's what, like all the colors of the rainbow are what we can actually see. So if you think of infrared, like that's going to be less than red, so that's going to be lower than red. Then if you get into like ultraviolet rays, that's above our visible light. Just have an idea of how fast the frequencies of these different things that we can see are actually moving and stuff. 532, Factors affecting infrared imagery. The sentence before the bullet points is highlighted. Objects can appear to be cooler or warmer than they actually are because of the following factors. And I've got the first bullet point, the emissivity of the object. Sensing equipment, 533. The sentence that's before that one bullet point all the way on at the end of page 41 is highlighted. The following are examples of infrared thermal inspection applications. And then I've got the second bullet point on page 42 highlighted. Motors, hotspots, and worn bearings. And then the last two are also highlighted. Transformers for hotspots and bearings for hotspots and wear. I actually like what this guy is doing with this little thermal camera. When I was an intern at Goodyear, like they made me walk around like the air compressor room and take pictures of bearings, and also go to like transformers. Transformers can get hotspots if windings have shorted together, or if different taps have not been terminated correctly. You can get hotspots in transformers, and you can see that through an infrared camera.
You said the bullet points is motors, what else?
Motors, transformers, and bearings. IR spectrometry. 534. The whole first paragraph and first sentence of the next paragraph are highlighted. Another use for infrared detectors is the science of spectrometry. Spectrometry is used to determine chemical composition of an object. If an unknown sample is analyzed using the spectroscope, the chemical makeup of its sample can be determined. In absorption spectrometry, radiations of a particular wavelength in the appropriate region of the electromagnetic spectrum are employed. 534. Good. All right. Just give me a couple minutes. Measuring ultraviolet radiation. Last. PowerPoints. 541 UV analysis. That second paragraph, the whole thing's highlighted. The UV absorption pattern of a compound is not so distinctive as a fingerprint as its infrared counterpart, and fewer compounds absorb the ultraviolet region than in the infrared. However, several important classes of compounds absorb strongly in the ultraviolet region. The next half of this sentence is a separate highlight that you want to key in on. Whereas water and the usual components of air do not absorb in this region. As a result, ultraviolet absorption analyzers may be more selective and sensitive than infrared and other types of analyzers. First sentence is highlighted. Compared to infrared analyzers, UV analyzers are generally more sensitive, yet they provide a comparable level of selectivity.
Where's that?
That is first sentence of 543.
Oh.
Compared to infrared analyzers, UV analyzers are generally more sensitive, yet they provide a comparable level of sensitivity. And my last highlight on page 44, flame detectors. Second to last sentence on page 44 is highlighted. Ultraviolet detectors are considered to be superior to infrared detectors in this area because they are not affected by radiation emitted from hot surfaces inside the furnace. So you use a UV scanner in order to see if there's a pilot light.
Wait, where's that at?
Second to last sentence on page 44.